Yeah, today I'll be talking about over-the-air update implementation, and specifically I'll be presenting the real demo of how that works, how it's implemented, and I'll be also talking about some theory behind this. The OTA topic is huge, is like really enormous, and even talking about some principles would not, one day would not be enough. So to cover that in that short time, I'll be talking about some subset, which is quite common in the microcontroller world, but by no means it will be an exhaustive talk. So before jumping into that, I'll probably just talk a little bit about myself so you'll know like who's talking to you. So let me do that. So I'm Sergey, and I'm an engineering director at Cesanta. Cesanta is a tech company in Dublin, in sunny Dublin, because today we have sun, uh, which is really unusual these days and really pleasant. So, and our mission is to create the best solution for making web dashboards on embedded devices. That's our specialty. That's what we do. And our main product is Mongoose Library. So Mongoose Library is something that you'll be seeing today, and which I'll describe today. Uh, and I'm a frequent speaker in all sorts of events, including big conferences like Embedded World. Maybe I'll speak next year, but I've gave talks like multiple times at various platforms. Another interesting thing is that I'm the author of Bare Metal Guide on GitHub. So if you're an embedded engineer and if you're interested in that topic, bare metal programming, you can check out my guide. I think this is the most popular bare metal programming guide on GitHub. There is no other guide that's as popular as mine. So that's the bragging. And so you can see it's 3,500 stars. So this is the guide. It's pretty exhaustive, and it goes from the very basic things like registers, what is the like memory maps, down to very complex topics like automated testing on embedded devices and so on. So recommend to check it out. And so this is me. In our company, we've been dealing with OTA for like more than a decade. So like we've collected a much experience in that. So Mongoose, what is Mongoose Library? It's basically a TCP/IP stack. So here you see it's an open source TCP/IP stack. Here you see it. It's also quite popular. It's like 11, almost 11,500 stars. And the cool thing about it is just two files. So it's like these two files are really easy to integrate in any embedded firmware code. And the cool thing about Mongoose is that it is self-contained, right? So it has an embedded TCP/IP stack. It has drivers. It has libraries for WebSocket, HTTP, MQTT, and it has TLS stack. That means that if you want networking on your embedded device, you don't need any other software. You don't need LWIP, you don't need drivers, you don't need RTOS, because usually networking demands RTOS. Mongoose does not. So it works on RTOS and without RTOS, and with RTOS the same way. So that's what Mongoose does. And the most frequent use case, at least for our customers, is to implement device dashboards, right? So implementing device dashboards, and we've built a tool to making that really, really easy. And over-the-air update is something that almost always comes with the connected device. So if you're making a connected device, that question about updating the firmware, it usually comes like sooner or later, usually sooner. So it's basically one of the things that always accompanies the connected device. And that's why in the OTA support is built in Mongoose, right? So Mongoose has a built-in support for the OTA for a wide variety of microcontrollers, for most popular microcontrollers. And most popular these days, if we're talking about the general purpose micros, are STs and NXPs. They roughly take about like 90% of the market. So and that's what I'll be covering. So in my demonstration, I will use ST development board and show how OTA works there. So now what I think I'll do, like this, the presentation goes into the theory. But before jumping into theory, I want to show how that works as an end result. So I'll show you Mongoose Library and Mongoose in action, how it works. So for that, I'll stop presenting my slides and start presenting my whole screen. And I will do like things step by step in front of you and demonstrate over there update. Right, so let me do that. So I stopped my presentation, and now I want to share the whole screen. Let me do that. So now I'm sharing the whole screen, and you should be able to see my desktop. And if you don't, please let me know. So you should be seeing my whole desktop. So now what I have here, I have this is a Nucleo development board, Nucleo F756. But it could be any development board from ST with the built-in Ethernet interface, right? So it has Ethernet interface connected to my local network, and it's with the USB. Through the USB, it's connected to my workstation. So this is a development board which is connected right now to my laptop, right? And I'll be using this dev board to demonstrate the OTA, right? So let me do that. First of all, I go to mongoose.ws. This is the website for Mongoose, for our product. And I click on this big blue button, which directs me to the Mongoose wizard. So this is a tool to create web dashboards on embedded devices, right? And let me start a new project. So I start a new project, select create new C and C++ project. And here, this wizard asks me to select the output directory. So I select the output directory. I choose like work wizard. So this is my directory on my laptop, work wizard. It's empty right now. So I choose this empty directory as output. So this tool, this web tool, will generate a working project inside my selected directory, right? And now it asks me for the target architecture. So, and there is a like big variety of built-in kind of development boards for various microcontrollers, but that's not an exhaustive list. If you have Mongoose works on pretty much any microcontroller. So it's just it's a subset of supported micros, not the exhaustive set. So I have F756, so I select that. So, and now I can choose the IDE. So as you can see, there is a choice of IDEs. I can use a plain make project. I can use Cube. I can use Kyle. I can use Zephyr. Say if I use Cube, I can also select, is it a bare metal project or FreeRTOS, and so on. So, but let me choose the most simple case, which is GCC, just plain make project and bare metal, like no OS, just the minimum possible, right? So GCC plus make and bare metal. So I click next, and now wizard tells me, okay, select like a pre-built dashboard you want to use, blank or just with a single LED toggle, or a default dashboard with lots of stuff. So I choose default dashboard with lots of stuff, click next and click finish. Okay, so that's it. I have this kind of project generated for me. Now, if I click on Generate C and C++ project, if I click on this button, now my directory on my workstation is populated. So now it's not empty. It has files, right? And these files, they contain a working project for my board that I can build and flash. And I can do it right now. So I can type make. Now this make command, it builds firmware. So it builds firmware files, right? So I can list. So there are like firmware.bin, firmware.elf. So now I have a binary. So, and I can do make flash. So make flash invokes a standard ST utility, ST programmer CLI to flash this built firmware to the board. So now it's flashed, right? And as you can see, this default firmware, it blinks this green LED just to show that it works, right? And I can attach the serial monitor to the board just to see the output. So I'm using my like port, serial port and speed 115200, right? And let me now, how can I like rearrange? Let me reboot the board. Well, I'm rebooting the board and I see the logs and I see, okay, that it got an IP address from the DHCP server. So if I copy this address and enter into my browser, I can see the login screen. Okay, by the way, let me disable this login screen. So I go to settings and disable login authentication, disable serval, disable WebSockets. All right. So okay, and generate again, and then make flash again. So let me rebuild and reflash this project with those things, distracting things removed. Okay, so now I reboot the board again, refresh it, and now I don't have this login screen, just I don't want to type things. So now I have this default dashboard, which looks exactly like it was in the wizard, right? So the wizard allows to change things quickly and add new controls and so on, but we won't do any of that because the default dashboard has firmware update screen, which works straight away, which works without any any extra effort. So it has this firmware update button. And maybe just to demonstrate how easy to do that, maybe I shouldn't use the default dashboard. Let me use the kind of like blank dashboard from the very start. So let me select blank dashboard. So this is a really blank dashboard. There is nothing. So it's an empty firmware with no functionality. So now I'll drop a few containers. I'll drop a panel here with stuff. So I don't want this. I don't want this. I want firmware update button. That's the only thing I want. So I remove all the buttons and I add the firmware update button. So here is update firmware button, right? And I change this to update firmware. Update firmware. And that's it. So the update firmware button is linked to the API variable, a REST API firmware update, which I don't have right now, but I will add it soon. So firmware update API, which is of type OTA. And that's pretty much it. So here we go. I've just constructed a dashboard from scratch and added the firmware update button support. Okay, so I click on generate firmware. Now let me rebuild this. Let me keep the this thing running. So I'll just do make flash to rebuild and reflash the firmware. Okay, and now it's rebooted, and now I should see. So this is the real device. As you can see, this is a real device. I connected to this 192.167.3.64, and it shows me this one single thing, update firmware button. So now let's use this firmware update to let's make a change to firmware. Let's change something. And instead of reflashing the firmware from the command line, we will use this OTA button to update it remotely through the web interface. Right, so let me go and change something. So say I want to, like add something. I want to add another panel here. I want to add another panel, and yeah, just some panel with save button, which does nothing, right? So, and that's it. And I want to make this panel, say I want to make a background of this panel, yellow, for example. Let's make a yellow background. Okay. Make a yellow background. So we can see this is something new, okay? So I click on the buttons to synchronize my changes. And now I type make build. So I do not do make flash. I'm not flashing anything to my micro. I'm just rebuilding the firmware. So now this firmware.bin in my directory is a new firmware, which is a rebuilt firmware. So now what I do, instead of refreshing this, I go to the device and I click on this update firmware button and I select this work wizard firmware.bin file to update it. And here we go. So you see the button is spinning. The logs are showing stuff. Some update is going on. So let's wait until it's finished. Now it's swapping the partitions. I will explain later like what's going on. So it's done. And now you see it's rebooted, refreshed automatically. And here we go. Like we have a new firmware. We see new stuff. So as you can see how easy it is to update things remotely with Mongoose. And yeah, I did it through the web UI, but the underlying mechanism, the updating procedure, it works absolutely the same way without the UI, just using the uh, the RESTful like GUI-less interface. It will work absolutely the same way through, say, MQTT link. So like you can do it remotely through internet, not through the local LAN, and so on. So yeah, so now the demonstration is over, and now I want to kind of go through the theory about these things. So how these things really, really work. Oh, I see. Yeah, that's if there are questions, like please note them. I think we can have we will have a Q&A session afterwards. So now I'll go through the theory of stuff, and let me switch to the slides, back to the slides. All right, so when we are talking about the firmware update, what essentially happening, usually all microcontrollers have like, a flash. It could be internal flash, or it could be an external flash. Specifically on these ST microcontrollers, as you can see, like these are like big guys. And flash takes a lot of die space. So usually if you see a big microcontroller, then it means, like it has like a lot of internal flash. Like this ST microcontroller. It has like 2 megabytes of built-in flash. Some microcontrollers, they don't have built-in, they have external flash. For example, a notable lines of microcontrollers are NXP IMXRT. So this is a series of microcontrollers with which are extremely high performance microcontrollers. If you're familiar with, say, Teensy 4 development board, it uses one of those. It uses IMXRT 1062. But those microcontrollers are really, really high performant and fast. For example, this IMXRT series, they use Cortex M7, and they have like clock speeds up to 1 gigahertz. Like they are beasts. They are absolutely beasts. They have like a lot of RAM, a lot of CPU power. They can run Linux. So these guys, Cortex M7s, they easily run Linux. But if you look at them, they are smaller than this ST. They are more compact, and that gives a hint why NXP was able to do that, because they basically threw away the internal flash, and that gave them space and ability to make the core itself like really high performance. So yeah, but regardless of whether the flash is internal or external to the microcontroller, it's just a flash. That's where the firmware is stored, and usually, so you have your flash and you have your firmware. The firmware typically resides at the beginning of the flash. Why it resides at the beginning of the flash? Because and we are talking about ARM microcontrollers here, so we'll probably, like, a lot of which I will say will probably also be applicable to other micros, like to other architectures like RISC-V. But let me be clear. I'll be talking about ARM. So in ARM architecture, at the beginning of the when the ARM microcontroller starts, it starts in order to operate, a microcontroller needs two things only, right? It needs two things. It needs to know what is the address of the instructions to execute, right? So it's the entry point of the firmware. So it needs that number. What is the address? What is the entry point? And the other thing that it needs to know the stack, the top of the stack. Because like the microcontrollers, they use stack for lots of operations, like calling functions and so on. So they need to know the top of the stack. So these two addresses a microcontroller should know, and that's why all our microcontrollers, they have a so-called this vector table, like in two entries in the vector table. These are two numbers, right? So one is the entry point of the firmware, and the second number is the stack, top of the stack, right? So that's why the firmware binary is typically at the beginning of the flash, because when the micro starts, it starts reading these two numbers from the beginning of the address space, from these like address 0, and usually that address 0 is mapped to the flash area, right? So when the micro reads a address 0, it usually reads the very beginning of the flash, and the very first 4 bytes is the entry point, and the next 4 bytes is the top of the stack. So that's the very usual kind of layout. And then after the vector table, like after these two entries, the top of the stack and the entry point, there is the rest of the vector table, which is like just a list of addresses of interrupt handlers. And then we have like the code, the code and the data of the firmware. So that's the structure of the firmware. And the rest of the flash is empty, right? So now we need to basically update this firmware to something else, okay? So what we usually do? So the first thing that comes to mind is just to copy this firmware elsewhere on the flash. And like the typical solution is just to split the flash in two spaces, right? In two partitions, and copy the new firmware to the second partition. So, and here in this kind of image, we have like firmware 2 in green, which shows the second partition, right? So, and usually, so when you have now two firmwares, like the old firmware and the new firmware, when you start your microcontroller, you need to know, okay, so what is the new one? What is the firmware I need to execute? And here is where the so-called bootloader comes into play. So the bootloader is the piece of code that decides, which firmware to boot, like which firmware to execute. Obviously, bootloader can do other things as well, but that's one of the primary kind of tasks of the bootloader. So the bootloader goes to it resides at the beginning of the flash, right? So, and there are like two ways of implementing this bootloader, as you can see on the kind of diagram 3 and 4. So one way is to have the bootloader at the beginning of the flash, and then this bootloader never gets updated, right? So it never gets updated, it's always there. And what you can update is just those yellow and green parts. So you can update those firmware binaries, but never the bootloader. And the diagram 3, it shows the situation where the bootloader is actually embedded at the beginning of the firmware. So the firmware begins, the firmware's entry point is actually the bootloader, right? So in this case, like the firmware in the yellow firmware always, it decides which firmware to boot. So the yellow firmware can decide whether it should execute the yellow firmware or the green firmware. So it can jump to the green firmware. And if the green firmware then gets the control, and it decides to update and write the new firmware in place of the yellow firmware, now the bootloader can be updated in this case, right? So the firmware update procedure by default a priori can update the bootloader itself. So in this scenario, imagine that we have a new version of the firmware on the second partition, right? So and when we have it on the second partition, that way, that scenario, that OTA scenario can obviously work, but there is a catch with this. The catch is that, like, look, like here, look at the at the diagram 2. So the yellow firmware and the green firmware. Imagine that we update it to the green firmware, and now, like, we want to start executing the green firmware. The problem with this approach is that when we create a firmware, when the binary is created, this binary is always linked it's linked against some starting address, right? So all the functions in the binary, they have their like absolute addresses. Like, for example, if you have a function foo that calls a function bar, both functions, they have absolute addresses in the firmware image. And when a function foo calls function bar, it actually is, it's coded like the language, the binary code, it goes something like this, like jump to this address or call this address, like an absolute address, right? And that means that if firmware 2, if the green firmware was built the same way as the yellow firmware, so that means that if it thinks that it is linked to the beginning of the flash, then the very first call of the very first function of the firmware 2 image would jump back to the beginning of the flash, right? So I guess I would love to ask the audience about, like, have they heard about the linker script and how that things work? I could show how that really works. The linker script. Let's see, we have like 30 minutes, but I probably can do that. Like, look here. So we have like firmware code, a firmware code here. I'll probably describe this linker script because it's rarely described, and sometimes people do not understand how linker script work. So this is the source code for my firmware, right? And inside that source code, there is a file called link.ld. So the files with the extension LD, that's a linker script. And that linker script, if I open that file, link.ld, it basically shows me the layout of memory of my microcontroller. Um, Usually there are like, there is a flash area. It could be one or it could be several flash areas and the RAM areas. In this specific micro, there are two areas, one flash and one RAM. So as you can see, flash area starts at one address and RAM area starts in another address, and they have different sizes. And the rest of the instructions of this linker script, it tells like which pieces of compiled code should go well, like should be linked against which addresses, right? For example, it says like all the code of this firmware, like all like text code should go into flash area. And the first, like, and the flash area should begin with the, with the piece of firmware which is called vectors, right? So the vector table goes at the beginning of the flash, then goes code, then read-only data. And after that, we have like our data sections, all our variables and stuff like that. It goes into RAM area, which also get concatenated to text and stored in flash, right? So this file is basically tells how the absolute addresses should be assigned to function and variables. And I can show that show you that. Like, for example, the compiled binary for this firmware is called firmware.l. If I do arm EAB, I think it's objdump, say disassemble the firmware.elf, right? So if I disassemble this binary, then I can see the functions inside my firmware. So for example, function main. And as you can see, this function main is located at this address, right? At this absolute address, which goes like 8000000, like 281 or 218, right? And you may wonder where that number comes from, like why it is like this, right? And it comes from the linker script. So the linker script says like all code, it should go to flash, and flash starts with this address, okay? And that's why when we create a bunch of functions, they are all kind of got linked to this address, right? So and like there are other functions. So you can see they are all assigned addresses, which basically go to the beginning of the flash, but not at the very beginning of the flash, because at the very beginning of the flash, there is a vector table, right? Which is not shown by disassemble command. And if I look at the, at the variables, I guess like we have like variables in our yeah, like there are variables. So all the variables are really linked against the RAM addresses. So, and RAM addresses are here, like they start with this address. So, and now when we create another firmware and we want to, like this green firmware to work from the second partition, we need to change the way it's built, right? So that's my like the main point why I'm talking about these linker scripts and the layout is that this simple fact, there is a strategy, there is an OTA strategy that copies the next, like the new firmware to the other partition, to the free partition, non-active partition, right? So in this case, it's second partition. And if we want this firmware to work, it should be linked against the middle of the flash. That's the point, right? So essentially what we need to do is we need to create another linker script file. So we need to copy the linker script to the linker2ld, right? And then in that linker2ld, we need to change the origin of the flash to something else, like to the middle of the flash. So now we have like 1 megabyte flash, and the beginning of the flash is 512, which is in hexadecimal, I don't know, like I don't know what's the right number, but let's say it's like this, right? I'm sure I'm wrong, but you get the idea. So we change the origin, and then we rebuild the firmware. So clean. So let's see how the firmware is built. Like the firmware is built using this linker script, right? But if I copy this command and change the linker script to link to LD, right? I've built another version of the firmware which is linked against the like middle of the flash. Now the compiler tells me, yeah, like yeah, there is some warning. I don't really see what don't understand what that warning means. But now this firmware.elf, it's linked against the other origin of flash. It links against the middle of the flash. And if I object dump, if I disassemble the firmware again, you can see that my main functions and other functions now start from the middle of the flash, not at the beginning of the flash, right? So the bottom line is then when we go with this strategy of firmware update, when we want our new firmwares to work from the other partition, we need two different builds for our firmware. As you can see, I did not change the functionality. I did not change the C code. What I did change, I just changed the linker script. So I changed the addresses, all the absolute addresses in the build. And in this strategy, what is important to do is just to understand that the firmware could be linked against different addresses. And if we want to use this strategy, we need to make sure that we copy the right firmware into the right partition. So all the firmware binaries that are linked against the beginning of the flash, they need to go to the beginning of the flash. And the firmware binary that needs to be on the second partition needs to be linked against the second partition. Otherwise, the very first call instruction or jump instruction will crash it, right? So this summarized this whole thing. This OTA strategy is perfectly possible. It's utilized in real life. I've seen cases like production cases where it's used. The cool thing about this strategy makes it a bit more difficult to manage the firmware. So you need to be careful. You need to maintain two builds, two binaries of the same firmware, and you need to be careful to copy over the correct binary to the correct partition. But it makes the bootloader very, very easy to write. Because all bootloader needs to do, it needs to figure out, okay, what firmware is newer, right? What is the old one? What is the new one? And when it decides what is the new one, it just jumps there, and that's it. So that's all the bootloader does. The bootloader code becomes really, really simple, and since it is simple, it's really difficult to make a mistake in the bootloader, right? So it's really robust. So this mechanism is really robust, but it's kind of like a bit more maintenance, right? So what would be like the other scenarios of the over-the-air update? The next simple scenario, which is possible, is when your firmware is really small, like really tiny, right? Or your RAM is really huge. So basically, your whole RAM can, you can copy the whole firmware into your memory. Like you can buffer the whole firmware into memory. So, and when you buffer the whole firmware into memory, you don't need to store it into the second partition or anything. You have like the whole thing in memory. And now what you can do, you can just copy this over to the beginning, like to the beginning of the flash. So you can just get this new binary, just copy it over to the beginning of the flash. That's it. That's the simplest possible way. What could be the catch in this scenario? Like, first of all, the copying function should be resident in RAM, right? So it should be RAM resident. What it means, like usually when we write functions, they are stored in in Flash. And when you execute the function, when the microcontroller executes the function, it reads the instructions of the function from Flash. So imagine that you have a function that copies, firmware 2 to firmware 1. And the code of this function is actually in firmware 1 area, right? So the function will essentially erase itself, like it will kill itself. And in Flash, like when we work with Flash, we cannot just simply write to things. We need to erase the Flash beforehand, right? So the Flashes work sector by sector. If you want to write something, you need to erase the whole sector first, everything, and then you can write. And you can write once, right? As soon as when you wrote something, that's it. You cannot rewrite it. The only thing you can do, you can erase the whole sector again and write again, right? So, and imagine our copying function needs to clear the whole sector at the beginning of the Flash, and now it kills itself. It kills, it kills its own code. Now the microcontroller cannot proceed, right? So because the function removed itself. So the function should be in RAM. And how it's done, I can also show how it's done. So the way it's done is that, look, so we have here an example, like for example, function blink timer. It's linked against, it's in the beginning of the Flash area, right? So imagine that function blink timer. We want to use that function. It's basically copying the firmware to the beginning of Flash. So that's our copy function. We want to make it RAM resident. So what are actions? How we can do that? Again, we can do that using a trick. All right. So we can use our link to LD, right? And in our link to LD, we have to have the special name for the compiler for the code sections. So we need to just give a name of a certain section. Like in this case, it's IRAM, right? Instruction RAM, but it could be something else. It could be like say blah. So we can give it the name blah. So, and that means that all the sections that are put in that, like everything that we put in that section blah will be placed into and linked against the data region, right? And data region goes into RAM, okay? So now as we have this kind of like linker script instruction, we can go and change our main function, and we can say that, hey, this blink timer function, we want to put it inside the section called blah. And I think I think it's like this section. I think it's called like this. So this is I forgot what is the right syntax for this, but I think it's like that. So you basically hint the compiler, linker, right? So they hint the linker that this function should actually go to the elf section blah, right? And let me rebuild it again. So I build this binary again. And now let me disassemble. And as you can see, I do not see the blink timer. But if I search for blink timer, you can see that the blink timer function now has address very high. So this address definitely belongs to the RAM section. You see, it starts with 2, right? So it's in the RAM area. So now what we did, we placed our function into the into RAM area. So now it's RAM resident, right? So and this way is basically you can do this trick. So if you have a huge RAM, you can just copy over the whole firmware to the beginning of the Flash. but you need to make your copying function RAM resident. You need to disable all interrupts during the process. Because why? Because interrupts are also coded in the vector table. They are at the beginning of the flash, right? And the MCU reads the addresses of interrupt handlers from the beginning of the flash. If your procedure like just clears that vector table and writes the new one, obviously, like the current interrupt, like if you get an interrupt, MCU will go like and see, okay, what's the address of the handler, and it's some new address, and there is nothing there at that new address, so it obviously will crash. So you need to disable all interrupts. You need to have the copying function RAM resident, and yeah, if it crashes during the process or if it powers off, you're done, right? So it's gonna be bricked. But otherwise, it's a really easy way to do the update, right? If you have plenty of RAM, just don't bother. Just copy it over to the beginning of the flash. So that's the next strategy. The next strategy is to copy to the second partition and swap. The cool thing about this strategy, and by the way, it's the one that is implemented on this board, which I just showed you, right? So it has like 1 megabyte flash, and we kind of like split it in two. We copied the firmware to the second partition, and then we swapped it. So we swapped two partitions. So what it gives, like what's benefit, what is the benefit from having the swap functionality? The benefit is that the new firmware can be exactly like the old firmware. You don't need to have an extra build. You don't need anything. So you just build it the way you usually build. And that's what we did. In the demonstration, as you can see, I did not do any tweaks. I just updated, like had an updated code. I just built it, and that's it. I got the new binary. So, and that firmware 2 binary is linked against the beginning of the flash. So when the OTA procedure ends, what happens next is at the end of the copying, we need to swap the partition. Again, we need to kind of disable all interrupts, have this swapping function in memory, and then we copy kind of sectors from second partition to the first partition. And that way we copy the firmware 2 at the beginning of the flash. And it works. So it boots and works as usual. But again, interrupts must be disabled and no power offs. So if there is a power off, the device will be bricked. All right, so this is the kind of like next scenario. And the easiest is the one which is using dual bank flash. So what is dual bank flash? This is the technology used by flash creators that split a flash into two partitions, right? So they split it into two partitions. But in the flash controller, they have a special bit, and that bit says how that these two flash partitions are mapped into memory, right? So there is a usual order, like the right order, where the first partition is mapped at the beginning of the flash, and the second partition is mapped after that. But you can swap that bit, right? Swap that a kind of dual bank bit. And after that, if you reboot the box, the second partition or the second bank, they call it a bank, not a partition. So the second bank would be mapped first, and the first bank will be mapped second. So in this case, what you can do, you can copy over the second firmware to the second bank, right? You can just copy to the second bank, and then just swap that bit in the flash controller and reboot the box and do nothing. So you don't need to do like physical sector swapping. After you've rebooted the box, the second bank will be mapped at the beginning of the flash, and the firmware 2 will gain control, right? So this is the way, and this dual bank support was primarily created for these OTA procedures, right? So and also it gives like an easy way to roll back the firmware. Like if you want to roll back, again, the only thing you need is to swap this bit in the flash controller and you've got the old firmware. So this is the kind of like the most modern, the best way to implement the OTA. So again, yeah, I won't go into details in describing how like copying from network works. So this is pretty much it. So that's the end of my overview. As you see, I gave like 4 possible strategies, 4 scenarios for the OTA. In reality, there are like thousands of them, like really thousands, like a lot of ways to, like, you can combine those strategies. You can use like external external storages and so on. There are endless possibilities, but these 4 are most common, especially for those kind of micros that we are talking about, like STs and NXPs with the built-in flash. It's like most common. So yeah, that's pretty much it. That concludes my kind of theory session. And now we've got 5 minutes to go. I'm ready for the questions if there are any.
Well, thank you very much, Sergey, for a very enlightening talk. So I'll jump right into questions because we only have 5 minutes. I have a question here from John, and they'd like to know about how to handle rollbacks if your update doesn't go correctly.
Yeah, so rollbacks, I touched on this thing in the uh, just a minute ago about like when I talked about dual bank flash, right? So the usual way, at least what we found, like there are multiple ways of handling rollbacks, right? What we used a lot, actually a lot, and which proved to be work like really, really nice is this. You have to have a bootloader code that installs a hardware timer, right? So it installs the hardware timer, which triggers at some point, like say after half a minute or a minute. And this hardware timer should check the something on flash, like a clean flag or commit flag. You can call it like you can call it the way you want. It's basically an OK flag, right? So if the hardware timer looks at that flag, so 1 minute after boot, and it looks like the flag is there, like this flag is there, then it continues on, like it continues with the firmware. But if the flag is not there, then it goes and it boots the previous firmware. And in case of the dual bank support, it just swaps the bit in the controller, right? And reboots the box. So it goes like and boots the previous firmware. If you physically swapped the 2 partitions, the bootloader actually should do that, right? It should go and swap the 2 partitions back and copy the old firmware to the beginning of the flash, right? And then reboot the box. So and after this, it works like pretty reliably. Imagine that you have so you have your firmware. It's like a golden firmware. It works fine, and now you replaced it with the faulty firmware, which which hangs, for example. In 10 seconds, it just hangs, right? So you copied that, and then the bootloader sets up the hardware timer, and after a minute, it obviously does not see this clear flag set, and it reboots. Okay, so it rolls back to the old firmware. If your new firmware is okay, like okay, so it's okay, it copies over, it works, then the first thing it should do is to set that clear flag, like set that golden flag. It could be manual or it could be automatic. The manual, it's usually, like a person that's doing the updated the firmware, then it sees, okay, so it's operating, it clicks the button, button click, it writes that flag to flash. or it could be automatic. The firmware could go to the website, download the, just access any website and see, okay, network works good, so I can do stuff. I set the clear flag. I'm fine. I'm good, right? So and in this way, so it works. So that's how the rollback works, and that's the algorithm of the pretty robust implementation. We use that kind of multiple, like hundreds of times. You can create like really faulty bad firmwares which hang, which like just don't work, and copy it over on production devices. They happily roll back. It works pretty fine, right? So this is the answer of the question. So use this specific kind of clear flag in Flash, and use the hardware timer to check it out.
Okay, and we'll just squeeze in one more question. I have a question here from Sarah who wants to know about signing your firmware updates.
Oh, the signing, that's the kind of worms. This is a really, like, this topic is probably like another hour. It's a big one, right? So I won't be able to cover this. It comes like it's a security thing. How do you make sure you're really updating to the firmware, which, how you make sure that this is not a hacker's firmware? That's the thing. And yeah, to be honest, I it's impossible to answer this like in a
No
minute,
worries. We
right?
can we can
So
invite you back in a few months to give another one.
yeah, it's a big topic. It basically talks about, like, we need to talk like a little bit about crypto, like what would be the hardware support for the crypto and so on. But the, like, not secure way, like the normal way, what you should do, your firmware should like check something, like check your website, for example, and then look, okay, so is the checksum for the firmware that published on the website is the same as you've just downloaded? Is it the same, right? So and it gives at least some a way of like checking like that you're okay. But even that mechanism, downloading the checksum and comparing, is not secure. You can beat it. You can obviously beat it. The real proper way is just to use like the sign, like, like a so-called secure update. And it's more involved like this. But at least what you can do, you can just check the check the checksums. So yeah, probably the topic for another talk.
Okay, and it's just gone past 2 o'clock, so I guess we'll close our Q&A section there. I just would want to thank Sergey again. And Sergey, maybe you can just give us a quick announcement on where people can go again to find more information about yourself and the library.
Yeah, so like this is it. Mongoose WS is the website. Like if you want to play, just click on this green button, and here you go. Like you can construct your dashboards and go to settings and select your device. You use, like, say, ESP32, go select ESP32. You use Arduino, choose Arduino, Raspberry Pi, whatever, like ST. Like you'll get the generated working ready to go project, and then you can play with it. So that's the easiest way to try to use it.
Okay, thank you very much again for the talk, and we'll leave it all there.
Thank
Thank
you,
you.
Jeffrey.